We will begin lesson 5.1, graphing exponential functions. The key concepts of exponential functions. The graph of an exponential function has characteristics relating to the intercepts, and we will find out that there is a specific intersecting point that's critical for exponential function. Also, the asymptote, there is an asymptote, and the domain and range. There are specific characteristics, the domain and range. Now, these are what an exponential function look like. There are two shapes to them, and today's lesson will be exploring these two types of exponential graphs. So, but before you look at exponential graph increasing, let's look at evaluating power because they're related. So let's do a review, and just in case you have forgotten, we have here in my display here exponential rules, and we looked at this yesterday. We have the product rule, the base is the same, we add the exponents. The quotient rule, the bases are the same, we subtract the exponents. The power rule, we have a bracket, we multiply the exponents. The power of product rule, we have the exponents are the same for both. The power fraction rule, the zero rule, this is the one we'll be using today. A to the 0 is 1, and a negative exponent, a to the negative exponent is 1 over a to the x. So these two will be focusing on today. And fractional exponent is the root of the base to the power of a numerator. Let's look at these examples. 5 to the power 3. This is your power rule, which means 5 times 5 times 5, which works out to be 125. Now, this follows the negative exponent rule, which is a to the negative x is 1 over a to the power x. We can rewrite that as a to the negative x equals 1 over a to the power x. So this will give us 1 to the 2 to the power 3, which eventually ends up to 1 over 8. So 2 to the negative 3 is the same as 1 over 8. 4 to the power 0 is what we call the zero exponent rule. A to the power 0 is equal to 1. This is also the negative exponent rule. So this is 1 over 1/3 to the power 2. Which is the same as 1 over 1 over 9. Now, if you were to work this out, this becomes 1 divided by the long way, which is 1 multiplied by 9 over 1. So 1/3 to negative 2 is equal to 9. So keep these in mind because we are going to construct graphs using the negative exponent rule and the power rule. Here we're going to complete this graph. But first we need to fill in the table of values. So y is equal to 2 to the power x, and you're given the values for x to find the values for y. We'll describe the graph including characteristics such as intercepts, equation of the asymptotes, domain, and range. So let's fill in our value. This becomes 2, -3, which is 1 to 2/3 with 1/8. So -3 would be approximately that point. 2 to the -2, which is 1/2 to the power 2, 1/4. -1 is 1/2, which is a half, to the power 0. And this is where you're using your 0 exponent rule. It's 1. To the power 1 is 2. 2 to the power 2 is 4. And 2 to the power 3 gives me 8. So now I construct a nice smooth graph by connecting these points. So this is my graph y is equal to 2 to the power x. Now, what are some of the characteristics of this graph? Now, we can see this graph is increasing. And we see it's increasing because as you go, as the x increases, the y increases. So number 1, the graph is increasing because as x increases, so is y values. That's what we mean by increasing graph. Now, notice your intercept. So we asked the characteristic of the intercept. The y-intercept is 1 or 1, 0, because that's your y-intercept. Now, this graph appears to have a horizontal asymptote. It never touches the x-axis. At y equals 0. In other words, there's no x-intercept. The domain, notice there's an arrow going up. The domain, there's no restriction. So we can see the domain is x, is a set of real values. Notice the range now is restricted because we have no x-intercept. Doesn't reach, there's an asymptote at y equals 0. So the range is y is greater than 0. Now, it doesn't touch it. We can conclude that this graph is always increasing. Because as you go from left to right, the graph is increasing. Now let's look at the reverse. We'll repeat what we did in the previous part B, but now we have y is equal to half to the power x. It's not an integer, but a rational number. So if x is -3, we have 1/2, and using our negative exponent rule, this becomes 1 over 1/2. Oh, there are shortcuts to these, but I'll showing you the long way, how it works out. This works out to be 1 over 1/8, and is equal to 8. Next, we have 1/2 -2, which is 1 over 1/2 to the power 2. It gives me 4. 1/2 to the -1 is 1/2 to the power half, 2, 1/2 to the power 0, which is our zero exponent rule. 1/2 to the power 1 is a half. One half to the power 2 is 1 over 4. And 1/2 to the power 3 is 1/8. Now let's plot our points. We have -3, -3 was 8, -2, 4, -1, 2, 0, 1, 1/2, 2, 1/4, and 3 is 1/8. Now, a nice smooth curve. And if you were to continue a table of values, find this graph never touches the x-axis. We can conclude, 1, as we did earlier, graph is increasing. Now, this graph is not increasing, it's decreasing. Notice as you move from left to right, or from increasing x-axis, the value in the x-axis, as the value of the x-axis increases, the y value decreases. So we say the graph is decreasing. As x increases, y decreases. Notice the y-intercept is at 1. So y-coordinate is 1, 0. It never touches the x-axis, so we see the horizontal y equals 0. And notice it's similar to the previous exponential function, the increasing one, the domain x set of real numbers, and the range, since we have a horizontal asymptote, the range y is greater than 0. Not equal to, it's greater than. So be careful about your graphs. So is not equal, then would never touch because of an asymptote of this. So so when we have, this is a fraction here or a rational number. When we have a rational number as our equation to the power of x, we end up with a decreasing function. Notice with a, what we'll find in the value a here is between 0 and 1 is decreasing. So compared to our previous one, when a is greater than 1, the graph is increasing. Now let's compare these two graphs, and I put them together here. Now, how are these two functions a and b alike, and how they are different? Notice they have a similar shape. You can see they're similar because they have similar shape. Y equals 2 to the power x is increasing. As x increases. Y half x is decreasing as x increasing. Now both functions, the y-intercept is at 1. One zero is our now both functions no x-intercept. That's the y-intercept. Horizontal y is at 0. And for both of them, the domain x set of real numbers and the range y is greater than 0. Now, I'd like to point out to you at this time that if we were to look at the ratio of consecutive y values, and if you go back to our first graph, notice the ratio between two consecutive y values is a constant. So if you go from 8, x8, sorry, x where x is 3 and x is 2, the consecutive 8 divided by 4 is 2. So we have 8 divided by 4 is 2. Then you look at the next one, 4 divided by 2 is also 2. So 8 divided by 4 is the same as 4 divided by 2. And if you were to continue, 2 divided by 1, they're equal to 2, 2, 2. So we can conclude that they have a constant ratio. if you look at consecutive y values, they have a constant ratio. So we can add that to our characteristics here. So both graphs have constant ratio. In other words, they're growing or decreasing at equal interval. Both are increasing or decreasing at, let's see, by a common factor. Over equal interval. So the ratio is constant. We have a constant ratio between consecutive y values. This is critical to know if you look at the constant ratio characteristics. Now the functions, what we've completed so far, are exponential functions. And to summarize, this is part of your booklet. In the first graph, we have a is a positive, which is 2. And in the first case, we have y 2 to the power x. When the a is greater than 1, the graph is increasing. When a is less than 1 and greater than 0, so we can say a is between 1 and 0, it's decreasing. And the other characteristic, both have y-intercept 1. The graph is increasing. The horizontal asymptote is the same. They have no x-intercept. The domain, x is set of real numbers. And the range, y is greater than 0. And the final one we add, there's a there for both of these, they have a constant ratio. And that's one of the ways you can find out if a graph is exponential. We look at the y values and find if there's a constant ratio between consecutive y values. We'll look at a couple of examples of this. Now, we have 3 graphs here, and the graphs of 3 functions are shown. Which graphs might represent an exponential function? How do you know? This is a quadratic, and it's a parabola. So it is not always increasing and not always decreasing, because it's doing both. It's actually increasing and a decreasing. So we can say this is not an exponential, because a function must be increasing or decreasing. And this graph is not always increasing or decreasing. So this is a parabola. So it is not always increasing or always decreasing. So this is not exponential. And here we have these two types of exponential function. Next, the shape is not an exponential because it's not increasing, and also the x-intercept, while the x-intercept here is 1, the x-intercept here is, sorry, the y-intercept here is 1, the y-intercept here is 0. So y-intercept is not 1 because exponential function, the y-intercept is 1. So this would be 1. This is not an exponential. The y-intercept for the next one is 1. And notice its graph is constantly decreasing. So this is an exponential function because it is always decreasing. And the y-intercept is 1. Also, the asymptote y equals 0. So the first is a parabola, so it's not always increasing or always decreasing. So it's not an exponential function. The second, the shape is not an exponential function because it's not increasing. And the y-intercept is not at 1. And the third, we have the exponential is an exponential function because it's always decreasing, and the y-intercept is at 1, with an asymptote at y equals 0. This assignment, assess your understanding. You may use a graphing calculator or Desmos. In your case, you may want to use Desmos. It's much more user-friendly than a graphing calculator. And complete this table. You will find that the domain and range should be the same. That's an activity for you to complete. We'll look at the last set of questions. And here, could each table of values describe an exponential function? Justify your answer. And this is where we are going to apply what we've learned earlier about ratio. So any exponential graph have a constant ratio, or is a constant rate of change. So if it's, it's a constant ratio, not a constant rate of change. So there's no constant rate of change, but a constant ratio between the y values. Let's look at this here. Let's look at the consecutive y values. We have 10, or we can go, we have 10. Let's look at the values here. 100, and the next one is 10. So these are my y values, y1, y2. So the ratio is 100 over 10. Gives me 10. Let's look at the next one. We have 10 and 1. 10, 1. Oops, there's be 10 here. Sorry, 10. 10 over 1 is 10. And if you're not convinced yet, let's look at the third one. We have 1 and 0.1. 1 divided by 0.1 is 10. So what we end up here with the exponential function. Because we have a constant ratio. Of consecutive y values. First one is exponential. Let's look at the next one. Apply the same rule. We can use 25 over 5. This is 5. And we look at the next one. We have 5 divided by 1 is 5. Go to the third one. We have 1 divided by 0.2 is also 5. And if you go throughout, you'll see it will be the same result. 0.2, 0.04 is 5. So this would be an exponential function. Another factor you can take into consideration when determining, look at the y-intercept. It's 1. Y-intercept here is also 1. It tells me right away it's an exponential function. The last question, although we have an intercept of 1, we're not too sure yet. So we'll apply our ratio rule here. Now let's look at the ratio between these two. 9 over 4. Now, get my wonderful calculator here and let's work it out. 9 divided by 4, 2.25. Let's look at the next one. 9 divided by 4, 4 divided by 1. It's 4. Then we have 0 divided by, 1 divided by 0. This is undefined. Zero divided by 1 is 0. There is no common ratio. So not an exponential function. So to conclude, our goal today was to investigate graph exponential function. And we found out there is an intercept. The y-intercept is 1, 0. The equation of asymptote is equal to y equals 0. The domain all the real numbers and the range y is greater than 0. We also concluded that when the a value on your exponent is greater than 1, it's increasing. When the a is between 0 and 1, is decreasing. So y is equal to a to the power x. And in our example, this overall view, and this is in your example booklet. And when we compared the two, we concluded that we compared the two, where decreasing or increasing, we have these similar characteristics. And we also discovered we have a concentration.